Right now, at this exact moment, Betelgeuse may not exist. The light reaching your eyes tonight left that star somewhere between the Black Death and the fall of Constantinople. It has been traveling through empty space for 5 centuries before touching your retina. You are not looking at a star. You are reading a message from a star, and you have no way of knowing whether the sender is still there. That should be a curiosity, a footnote in a physics class. The simple explanation is that light takes time to travel, and distances in space are vast. And this is just how astronomy works. That should have been the end of it. But in 2024, astronomers found something that had been hiding inside Betelgeuse's atmosphere for 10 million years. And once they found it, every measurement, every brightness reading, every model used to tell us when this star would die became uncertain in a new way. That is where the story begins. Betelgeuse sits at the shoulder of Orion. It is one of the largest stars in our galaxy, a red supergiant so enormous that if you placed it at the center of our solar system, its surface would reach roughly 3.5 times the distance from the Sun to Earth. Mars would be inside it. The asteroid belt would be inside it. The surface of the star would lie somewhere between the orbits of Earth and Jupiter. It is not a distant abstraction. On any clear night, without a telescope, you can find it. A red point, slightly warm in color, marking the hunter's shoulder. And it is dying. Every star this massive ends the same way. It burns through its fuel, hydrogen first, then helium, then heavier elements, until the core runs out of anything left to fuse. When that happens, there is no more outward pressure to fight gravity. The core collapses in less than a second. The outer layers slam inward at a fraction of the speed of light, then rebound outward in the most violent explosion the universe produces, a supernova. When Betelgeuse goes, it will briefly outshine every other star in the night sky combined. It will cast shadows at midnight. It will be visible in full daylight for weeks. That moment is coming. The question is when. And the question has become significantly harder to answer. In late 2019, something unusual happened. Betelgeuse began to dim. Not the normal rhythmic brightening and fading that variable stars do. This was different, deeper, faster than expected. By February 2020, the star had lost more than 2/3 of its visible brightness. Amateur observers noticed first. Then professional observatories turned to look. On social media and in conference rooms, astronomers began asking a question they almost never ask seriously. Is this it? Some suggested the dimming could be a precursor, that the internal machinery of the star was shifting into a final phase. The Great Dimming, as it came to be called, was not a scheduled event. Something had gone wrong with the most studied dying star in the sky, and no one was entirely sure what. The Hubble Space Telescope was pointed at Betelgeuse. Ultraviolet data began coming in, and within a year and a half, a team led by astronomer Andrea Dupree had an answer. In 2022, they published the analysis, a surface mass ejection. A massive convective eruption from the star's southern hemisphere had flung an enormous blob of hot plasma into the surrounding space. The ejected material cooled as it moved away from the star, condensing into a cloud of fine dust. That dust cloud had drifted between Betelgeuse and Earth, blocking the light. That was the dimming. The case was closed. It was a specific, physical, documented mechanism, not a sign of imminent collapse, but a violent surface event, the stellar equivalent of a wound healing over. Betelgeuse was recovering. By mid-2022, it had brightened back past its normal baseline. In early 2023, it reached the highest brightness level recorded in modern history, nearly 50% above average. Scientists noted this was likely just the normal pulsation cycle rebounding after the ejection. Unusual, but not fatal. The star was still here, probably fine, probably 10,000 years or more from its actual end. That should have ended the story. It did not. On December 9, 2024, a team of astronomers led by Steve Howell at NASA Ames Research Center pointed the 8-meter Gemini North Telescope in Hawaii at Betelgeuse using an instrument called alopeke. The technique is called speckle imaging, taking thousands of extremely short exposures and combining them to beat out the blurring effects of Earth's atmosphere. It is designed to reveal faint objects that would otherwise be drowned out by the brightness of nearby stars. What they saw was a faint blue point of light, right where a predicted companion star was supposed to be. For at least a century, some astronomers had suspected Betelgeuse was not alone. The star's brightness variations included a long, slow cycle lasting roughly 2,110 days, about 6 years, that did not cleanly fit the models of pulsation used to explain a single giant star's behavior. Multiple independent research groups had analyzed the radial velocity data, the astrometric wobble, the specific shape of the variations, and came to a similar conclusion. There was something orbiting Betelgeuse, something close. In 2020, the same instrument on the same telescope had imaged Betelgeuse and found nothing unusual, no companion. But 2020 was when, based on the predicted orbital geometry, the companion would have been passing behind Betelgeuse, hidden from Earth's vantage point. In December 2024, at the predicted moment of maximum separation, when the companion should be most visible to the side, the alopeke camera found a faint blue object at exactly the right position angle, exactly the right distance, with exactly the right brightness difference to match what the models had described. Its name, proposed by Howell's team and officially recognized in September 2025, is Siwarha, Arabic for her bracelet. It circles Betelgeuse, which derives from the Arabic for the hand of the giant. Siwarha is not a small rock. It is a star in its own right, roughly 1.5 times the mass of the Sun. It appears to be a pre-main sequence object, young, bluish, not yet burning hydrogen in its core, still contracting toward its eventual stable state. It formed alongside Betelgeuse about 10 million years ago, orbiting at roughly twice the supergiant's own radius, not next to it, inside its extended outer atmosphere. Think of it as a companion that has been swimming through the outermost layers of Betelgeuse for its entire existence, stirring the gas behind it as it moves, leaving a gravitational wake through the envelope of the largest star in our neighborhood. That detail matters more than it sounds. Every brightness measurement ever taken of Betelgeuse, every data point that went into the models used to classify its evolutionary stage and estimate how close it is to the end, was taken without knowing Siwarha was there. The 6-year variation in Betelgeuse's light, which astronomers had been using as part of the star's identity, part of its fingerprint, may not be intrinsic to the giant star at all. It may be the orbital period of a companion that nobody could see, and the great dimming from 2019 to 2020. It happened at the exact orbital phase when Siwarha would have been moving through its most obscuring geometry, when the wake of disturbed gas trailing behind the companion was, based on the orbital model, draped across the face of the star. The SME explanation remains valid. The dust cloud was real. But whether Siwarha contributed to the depth of the dimming, and how much, that is not a closed question. The companion was always there. We were looking at the wrong signature. Every model used to time Betelgeuse's death was built on an observation archive that did not account for a second star. The brightness record goes back more than a century. None of it was cleaned for a companion's influence. The models built on that record remain the basis for every estimate about where Betelgeuse is in its life. The case everyone thought was closed in 2022 has a new opening, not because the old answer was wrong, but because the old answer was built on measurements that were, without anyone's fault or knowledge, incomplete. The simple answer is true. It is just not complete. And halfway is where this becomes uncomfortable. Here is where the question changes shape. The surface mass ejection was real. The dust was real. Siwarha is real. Each of those facts fits neatly into its own explanation. The problem is what they do to each other. Because the discovery of Siwarha did not just complicate the Great Dimming, it reached back into every model that astronomers had built to answer the most important question about Betelgeuse. Not what caused one unusual dimming event, but where in its life the star actually is right now. To understand why that matters, you need to know how stellar aging works at this scale. A star like Betelgeuse does not age the way a human being does, visibly, progressively, with clear markers. It burns through fuel in stages. Hydrogen first, for millions of years. Then, as the core runs out of hydrogen, it contracts and heats until helium ignites. Helium burns for tens of thousands of years. Then, if the star is massive enough, carbon begins to burn. Carbon is the last long-burning stage. It lasts roughly 1,000 years. After that, heavier elements fuse in rapid succession. Oxygen, neon, silicon, each phase faster than the last. Silicon burning lasts about a week. After silicon, the iron core forms. Iron cannot be fused to release energy. When the core becomes iron, the outward pressure stops almost instantly. Gravity wins. The collapse takes less than a second. The difference between helium burning and carbon burning is not subtle. It is the difference between thousands of years of remaining life and something far shorter. In 2023, a team led by astronomer Hideyuki Saiyo at Tohoku University published a peer-reviewed paper in the monthly notices of the Royal Astronomical Society arguing that Betelgeuse's pulsation patterns and radius were only consistent with one interpretation. The star was already in the late stage of core carbon burning. Saiyo's team found that the specific combination of pulsation periods, the 2,100-day variation, the 400-day cycle, the shorter overtone cycles, matched models of a star that had already burned through its helium and was now running on carbon. If they were right, carbon exhaustion could come within centuries. After that, the collapse would follow in, as the paper stated, a few tens of years. The mainstream response was cautious. Other astronomers pointed out that Betelgeuse was too bright to match the behavior of late-stage red supergiants, which typically dim as they age. They argued that the 400-day pulsation, which most researchers treat as the star's fundamental mode, was better explained by helium-burning models, placing the supernova 10,000 to 100,000 years away. Saiyo's interpretation was not dismissed. It was peer-reviewed science, but it remained a minority position, contested by multiple groups with competing models. That debate was already unresolved when Siwarha was found. Here is the problem. The argument that Betelgeuse is too bright to be in its final carbon-burning stage depends on its observed brightness. But Siwarha has been orbiting inside Betelgeuse's atmosphere for 10 million years, stirring gas and scattering light as it moves. The brightness record that mainstream astronomers used to argue Betelgeuse was too luminous for late-stage carbon burning contains the orbital influence of a companion nobody knew existed. Correcting for Siwarha's effect on the long-term brightness record is not yet fully done. The research is ongoing. Future observations, including the next time Siwarha reaches maximum separation from Betelgeuse, predicted for late 2027, will allow deeper measurements. But right now, the main counter-argument to the carbon-burning hypothesis rests on data that is itself uncertain in a new way. The old answer did not fail. It became too small. Carbon burns slowly, but slowly still has an end. And this is where the story takes a turn that has nothing to do with instruments, or models, or companion stars, or dust clouds. This is where physics itself closes a door that no telescope can reopen. Betelgeuse is somewhere between 500 and 880 light-years from Earth, depending on which measurement method you use and which data set you trust. The best combined estimate, published by Graham Harper and colleagues in 2017, using radio telescope data from the Very Large Array and revised Hipparcos measurements, places it at roughly 724 light-years, with a 1 sigma range running from 613 to 881 light-years. That range is not a small rounding error. It spans 268 light-years. And 268 light-years is not just a distance, it is a duration. It is the difference between receiving a signal that left the star in 1145 CE and receiving one that left in 1413 CE. It is a window of nearly 3 centuries during which the star's light could have departed, and we would not know which end of that window we are sitting in. Think about what that means in human terms. The light you see when you look at Betelgeuse tonight left the star somewhere between the era of the Crusades and the early years of the Ottoman Empire, depending on where the star actually is. Those centuries contain the Black Death, the fall of Constantinople, the invention of the printing press, and the beginning of the Renaissance. The star has already lived through all of them since the moment that light left its surface. We are watching a message that was sent before Europe knew the Americas existed. And here is the irreversible part. Whatever stage Betelgeuse is in right now, wherever it actually sits on the carbon-burning clock, we cannot know. Not because our instruments are insufficient, because the information has not arrived yet. The star's current state is inaccessible. The light that could tell us where Betelgeuse is today will not reach Earth for centuries. That is not a limitation of technology. It is a law of physics. There is no instrument that can be built, no telescope that can be launched, that will tell you what Betelgeuse looks like at this exact moment. The universe does not allow it. If Betelgeuse collapsed into a supernova 400 years ago, sometime in the early 1600s, while Galileo was building his first telescope, the light from that explosion is somewhere between Earth and the star right now. It is in transit. It will arrive. We do not know when. We will have no warning. One night, Orion's shoulder will brighten into something that outshines every other object in the sky except the moon and sun, and the light carrying that information will have been traveling toward us since before the first modern scientific observations of the star were ever made. The sky is not a window. It is an archive, and some entries have not been filed yet. In June 2025, astronomers detected a supernova in a galaxy called NGC 1637, roughly 40 million light-years from Earth. The event was labeled SN 2025 PHT. Researchers cross-referenced JWST infrared images of that galaxy taken before the explosion and found the precursor star, a red supergiant hidden inside a dense shell of circumstellar dust that had made it invisible to optical telescopes. JWST, observing in infrared wavelengths that pass through dust, had imaged the star before it died. But here is the detail that matters. By the time JWST detected that precursor through the dust, the star had already been dead for 40 million years. The infrared data showed a pre-explosion state. The explosion was old news. The precursor observation and the supernova announcement arrived almost simultaneously from a human perspective, separated by the processing time of telescopes, but separated by 40 million years from the universe's perspective. Betelgeuse has its own dust shell. The surface mass ejection of 2019 left a cloud of cooling material surrounding the star. It is still there. If the precursor state of Betelgeuse's supernova has already begun, if the internal chemistry has shifted and the final stages are underway, the infrared signature may be changing right now, embedded in dust that scatters optical light. JWST can see through that dust, but JWST can only show us what the star looked like when that infrared light left its surface. If that light left 600 years ago, JWST is showing us 1425. Not today. Tonight, if you go outside and find Orion in the winter sky, the 3 stars of the belt, the bright blue-white of Rigel at the hunter's foot, and you move your gaze up and to the left, you will find a red point of light at his shoulder, warm-colored, faintly orange. The same point of light that people in medieval Europe saw, that astronomers in ancient Arabia named, that has been the most studied dying star in human history for centuries. The light entering your eye right now left that star sometime in the 1300s or the 1400s. Betelgeuse has already lived through 500 more years of its life since that light departed. It has already answered the question of which model was right, helium or carbon, thousands of years or tens. That answer is locked inside light that is still traveling toward us. You are not watching a star. You are watching a message from a star that may no longer exist. Right now, at this exact moment, Betelgeuse may not exist. That sentence opened this story as a provocation. It ends it as a statement of physics, not a metaphor, not a thought experiment, a genuine, unresolvable condition of our position in the universe, confirmed by the speed of light and the distance between 2 points in space. The star may be alive. It may have collapsed already. We are receiving its past. Its present is unavailable. Orion will rise again tonight, as it does every winter. The red shoulder will be there, steady, unchanged to the eye, reporting in from a time before telescopes. The archive is still transmitting. Whether the source is still there, that is not a question physics will answer from here. The light is old. The message continues, and we are still waiting to find out what it says.